I think I can hear them coming. It's so dark in here I can hardly see a thing. That's interesting. Difficult to tell them apart when they look like that. Excuse me, do you think we can have the lights on? Lights, please. That's better. Electromagnetic radiation at the flick of a switch. Well, after that, there's only one thing we can investigate today. Collect up all the most brightly colored things you can find, because we're going to experiment with light. Do you realize, without sunlight, there wouldn't be any colors in the world? Absolutely no colors at all. I mean, just look. Wouldn't it be a dull world without color? Wouldn't the kitchen be a drab old place? I don't think I much like the look of it at all. Let's see. Have you got some really brightly colored things ready? But take the color away, well, it's not the same, is it? Come on, cheer up. I'll start putting the color back, because without color, it's quite hard to tell what things really are sometimes. Look at this. Without color, is it a grapefruit? Or is it an orange? Could it be a lemon? But put the color back, and there's no doubt anymore what it is. And what about this? It's a cabbage, all right, but what sort of cabbage? A purple cabbage. Is it a green apple or a red apple? Could it be a yellow apple? Looks like a white mug to me. Oh. But what makes things have different colors in the first place? Disc number 2, please. Switching to replay. The colors we see are reflections of the light that shines on them. But all things don't reflect the same part of the light, and that's why they are different colors. You see, the white light from the sun is really a mixture of all the colors of the rainbow. Because leaves on the tree reflect the green part of the light best, they are green. The sky reflects the blue part best, and so on. And at night, when there's not much light, we don't see many colors because our eyes aren't sensitive enough. The moon is reflecting the white light from the sun, all right, but not very much of it. About 300 years ago, one of the people who investigated light was this man, Isaac Newton. He set up a famous experiment in his laboratory. He pulled the curtains so that only a thin beam of light could get in, and he made it pass through a prism. A prism is a triangular block of glass. Newton discovered that white light from the sun was really made of a whole mixture of colors, the colors of a rainbow. With a dish of water, we can make a rainbow here in the kitchen. In fact, we can do Isaac Newton's experiment. Yes, we'll need that mirror. Then we need a light shining through a little slit, like the slit in Newton's curtains. That'll do nicely. With the mirror in the water at an angle, you find the right place to shine the little slit of light at it so you can see the reflection. And look, the light has been split into red and green and blue. What does it remind you of?
Where the torch is shining, it looks like a rainbow. And around each object, you can see the same colours.
It's a homemade rainbow in a homemade water prism. These are the colours that Isaac Newton saw in his laboratory all those years ago. You can see these rainbow colours all over the place. Greasy washing up water in the sink, and there they are. The oily surface is splitting up the light, just as the prism did. Those are the colours that make white light. All you've got to do is mix them in the correct proportions. I bet you've all seen rainbow colours in bubbles. The thin surface of the bubble splits the white light so you can see all the colours that go to make it. Well, splitting up light is one thing, but how are you going to put it back together again? Yes, that's right. You've painted the colours of the rainbow on the cardboard whizzers, so get them going. The faster you can get them to go, the better the effect will be.
Oh, it's working quite well. Oh, yes.
See how the individual colours blend into each other? Now, depending on how accurately you put your rainbow colours on the disc, you could get a kind of white.
Makes a noisy hum, doesn't it?
I can do that too, with my electronic whizzer. Do you want to see? I start off with a few colours and spin them. Add a bit of green. Touch more orange. Dab more green. And there you are. All right now, are you ready for our next experiment? Okay, write your name down and we'll discover something else about light. And you'll need those mirrors.
Oh, all right. Right.
Make nice big letters.
Ready?
Now put your name on your foreheads and look at yourselves in the mirror. What do you notice? Yes, everything is reversed left to right.
The word's backwards.
And now take both your mirrors and put them together at an angle. Do you understand what I mean?
It's got a big cardboard there. Oh, yes. Let's try this. Put there.
Yes, that's right.
And put it there. No. Don't believe it. Well, it's still backwards. No, is it looking at one there? Oh, yes, it's Tom.
The first mirror that reversed your writing is now being reversed back again by the second mirror. You try, Tom. Now we know what mirrors can do, let's find out what a reflection really is. You'll need a mirror again, some wooden bricks, and a light.
That goes
Use the
on.
bricks to make a tiny slit and shine the torch through it.
That one. And a torch in the middle. These go.
That's right, at the mirror.
Move it in a bit there. Now, turn the torch on.
Good. Look at that beam of light. The reflection seems to go away behind the mirror at exactly the same angle as you're shining it at from the front. You can do all sorts of things with reflected light, even impossible things. Switching to replay. A candle in a glass. What will happen now? How on earth does the flame stay alight underwater? It's ordinary water too. You'll need that sheet of glass to find out. Prop it up straight. And you'll want the bricks again. Find the two that fit together. Those are the ones. Put one behind and leave the other where it is. And adjust it so the reflection fits perfectly over the little brick. That's good. Now, when you measure the distances, you'll find that they're both exactly the same distance away from the glass. One in front and one behind. You see, exactly the same distance. And that's an important clue that could tell you how the candle trick works. Look at it again. Okay, girls, show them how it's really done. The candle in the water isn't alight at all, of course. The one that is exactly lined up with it on the other side of the glass. And you've been looking at the reflection of its flame carefully adjusted, so that it seemed to be in the right place. All done with reflection. Good trick, eh? A new experiment ready? The lighted candle and cardboard with slits. Use the brick to prop up the cardboard. Now line up all the slits so you can see the flame through them. That's it. This experiment will find out if light can go round corners. Are you ready? Now move the yellow card to one side. Flame gone. Try it with a different card. Well, I think you've proved that light travels in a straight line. But is it ever possible to bend light? Have you got those bottles ready? And the cardboard slit again? Now switch the torch on. And here's how you can change the direction of light waves. Line up the bottles so the light shines through them, and see if you can find out where the beam comes out. Have a look, Celia. Can you see? Put your finger on the place where you can see the light coming out. There.
Right.
Is that a straight line? No, it's way off. The light has definitely been bent. You can see it.
Because the liquid. See? But I bet you...
Pass that little dish, please.
Alright.
And put it on a couple of bricks. Now, put a coin in the bottom of the dish and put it in a place where you won't be able to see it.
About here. A bit higher. So I can actually see.
The edge of the dish is blocking your view. Good.
No, get up a bit. So you can see this bit of the tray. Can you see it there? No. Don't look. I can't.
Now, fill the dish with water. No, it's not floating. The water is actually bending the light that's reflecting off the coin, and that's why you can see it again. So sometimes light does bend when it passes through things like liquids. Here's another way to see it. Put a pencil in water and suddenly it looks as if it's got a kink in it. When light passes from air to water, it actually bends. The light is reflected in a different way. That's why lenses work. Rays of light passing through the glass lenses bend just as they bend when they go through the water. And once you know how to bend light with lenses, there's no end to the things you can do. All you have to know is what the different kinds of lenses will do to the light.
One that bulges outwards.
What does it look like?
Everything gets very big and blurred.
That's called a convex lens. What have you got, Tom? Yours curves inwards, doesn't it?
Yes. And everything looks smaller than it really is.
Swap them over for a moment and have another look. What do I look like through that lens?
You look very, very small through this one.
Okay, a ruler and a lens. And stick the lens on firmly with plasticine because you've got to find the exact distance the lens has to be to focus a sharp picture. When you find that spot, it'll be called the focal length of the lens. Have a look, Piers. Try to focus the light coming through the trellis behind you onto that piece of card in front. It's a bit like a camera would focus a picture onto a film. That's right, Tom. Slide it along the ruler and see what happens. Good. That's a nice clear image of the trellis behind you. Now, check the distance the card is along the ruler.
About 20 centimetres.
Right. That distance is what is called the focal length of the lens. Now, fold some card over a ruler to make a slide. And now we're going to use two lenses. Stick the lens that bulges outwards on the card at the end, and the one that curves inwards on the bit of ruler that's sticking out at the other end. Now look at me through the two lenses. Go on, slide the ruler up and down until you can see me clearly, until I'm in focus. Those lenses have turned me upside down. And as you slide it even farther, I get bigger. You know what you've made? A telescope. It's gathering all the light reflecting off me and then focusing it through the two lenses. But a telescope is also something else. Turn it around and look through the other way at that piece of plasticine on the table. Get it in focus again. Now, what do you see?
Very, very, very big.
It's enormously magnified. There are your thumbprints all over it. And with those lenses that way round, the picture is the right way up again. As a matter of fact, my assistant has got a very modern microscope in the laboratory. She's getting it ready to look at some tiny animals that live in the sea. They're in that drop of water on the glass plate. A microscope like this can magnify things thousands of times, but the way it works uses exactly the same principle as the ruler microscope you made just now. She's focusing it very carefully. And there they are, swimming about. Tiny single-celled animals called plankton, much too small to see without the lenses in a microscope. Disc 23, please. Switching to replay. One of the inventors of the microscope was a Dutchman called Leeuwenhoek. And this is what those early microscopes looked like. A bit different to the one my assistant has, isn't it? At last they could really see the tiny things around them, like this flea, which was one of the commonest creatures in the world in those days. And for the first time they could study it properly. Then this man, Galileo, turned the microscope upside down and looked through it and became one of the inventors of the telescope. 200 years ago they used telescopes like this. And today, astronomical telescopes are huge and complicated instruments capable of looking very far into the universe. And here's an astonishing thing. The light from these galaxies can take millions of years to reach us here on Earth. Right, so lenses gather up light and focus images for you to see through the very special lenses you have in your own eyes. This is a sort of lens too. Can you just make out those 3 upside-down candles? That's what they look like through a goldfish bowl. An eye is a bit like a goldfish bowl. It's the same shape, it's full of liquid, and you can see through it. The reason why everything is upside down is only because the bowl is a bulging piece of glass, and that's a convex shape. The lens in your eye is a convex lens, and all the things you see are upside down to start with. It's your brain that turns them the right way up. Ah, look at me, upside down through a convex fishbowl. The rays of light are reflecting my colour as they travel from me to you through the air and through the water. See how the water in the fishbowl is bending the light? And to think all the sunlight and white light in the world is really a mixture of beautiful rainbow colours. Now that's really something, isn't it?